glad that we moved the test. So on Wednesday, we sort of left the eye behind us. We've gone through the anatomy of the eye in quite a bit of detail. We spent a good part of Wednesday looking at the retina under the microscope, as well as using figures and at least one model in the lab to look at the microscopic anatomy of it. There's obviously a lot more we could have said about the retina. There's a whole lot of things about the sort of biochemical reactions that happen in those photoreceptor cells to create excitation so that we can send a message to our brain. But given the time that we have, I think that we sufficiently covered it. So what I want to do today is I want to go ahead and move on to the ear. And again, the idea here is that we'll get through a good chunk of it today, and then what we'll do is we will be able to finish it on Wednesday of next week. All right. So before I can really start talking about how we hear, I do need to start talking a little bit about the structure of the ear itself. Generally speaking, the ear is divided into three primary parts. We see that we have an external ear right here, a middle ear, and an internal ear. So let's go ahead and take a look at those parts really quickly. So we have an external ear. And a middle ear. Inner ear. The idea with the ear is that we're going to need to capture sound waves, and we're going to need to essentially turn them into a different kind of signal. Remember, ultimately, we need to send these messages to our brain, so they have to become action potentials at some point, right? So over the course of travel through our ear, we're going to go from sound waves to electrical signals in the form of action potentials that allow the brain to receive this message and interpret it as a sound. Okay. So how are we going to do that? The first thing that we do is we have to catch the sound wave to begin with, and that's the job largely of the external ear. All right. If you look at that diagram that I have on the board of the external ear, we see that one of the most obvious things about it is what you normally think of when you think of an ear. It's this thing right here, right? That external ear, the most prominent part of it is this flat of skin that we have here called the auricle or the pinna, right? So this is what we have right here. We have this auricle or pinna, which again, like I said, is what you probably think of when you think of your ear, even though it extends beyond that. It's the part that we see. It's the part that we're the most obviously aware of. What do you guys think this part does? What do you think the job of the auricle or the pinna is? Protection. Okay, it probably does provide a little protection. It's good at getting sunburns, right? But as far as hearing goes, what do you think that its job is? Acts as like a funnel, right? It catches sound, right? Its job is to act as a funnel to catch sound. I think we can all prove that to ourselves really easily. If you guys would humor me, let's go ahead and just make our auricles bigger for a minute. Go ahead and do this for me. If you do this, if you do that and I start to talk, do you notice a difference in terms of the loudness of the sound? Maybe a little bit? Okay. Yeah, right? I wasn't talking any louder at all, but when you do that, the sound becomes louder because you're catching more of those sound waves and you're funneling them into your internal ear. Right? You can do the opposite, right? We can also sort of deflect sound. We can make the funnel go this way instead. And when you do that, it makes it to where you can't hear as much or as easily. I think I inadvertently lowered my voice when I did that. I didn't need to. So I might have amplified the effect. But I think you guys get the idea, right? So it's definitely a funnel for sound. You know, if you look, if you have a dog or a cat at home or something like that, you'll notice that they have much bigger pinna than we do. And of course, well, first of all, they have a better sense of hearing in general than we do, but that really large pinna that they have is going to help them to funnel more sound into their ears. They can also move their ears, whereas we really can't, right? But you know, if you watch your dog, or I watch my dog all the time. If there's a dog walking down the street outside, boy, first of all, it's amazing to me that she can hear that, because that just, I hear nothing at all. But she hears it, she seems to know which dog it is. But you also watch the position of her ears change, right? They can change, like little radar dishes, they can change the position of their ears to be able to hear, right? So definitely, there probably is a protective function of the auricle, but its primary job is to act as a funnel for sound, okay? It is kind of, as you are well aware, there's cartilage in your ear. That cartilaginous ring around the edge of your pinna is called the helix. And then you have sort of the non-cartilaginous earlobe or lobule down at the very bottom down here. But it definitely is just a funnel for sound. Okay. The sound waves that we capture are then funneled into our external acoustic meatus. This is what you would normally just call your ear canal right here. But we're funneling those sound waves here into our external acoustic meatus. The external ear ends at this membrane that's stretched across the opening right here called the tympanic membrane. You can see the tympanic membrane right here. And in many ways, it mimics a drum. We'll talk about drums and things like that here in just a couple of minutes. But the job here is to funnel sound waves and bring those sound waves to the tympanic membrane. Those sound waves will ultimately vibrate the tympanic membrane, and we will be able to pass that sound on to our middle ear. Okay. I'm going to turn the lights on just for a minute here. And I'm also going to try to do this. There we go. Do that. So let's talk just for a minute about sound. On Wednesday, we talked about light, and we talked about the electromagnetic spectrum, right? We said that probably the biggest characteristic of the electromagnetic spectrum is that we're going to be looking at this thing called wavelength. Okay? Sound is very, very similar. Sound also travels in waves. Okay? Sound travels in waves, just like light does. And there's a couple of different measurements or things that we care about regarding the characteristics of a sound wave. One of them is the wave length. Okay, so we're looking as an easy point of reference. We're looking at the peak, the distance covered from the peak of one wave to the peak of another wave, right? This is what we call the wave length. Okay. I could have two waves with different wavelengths. You'll notice that the wave that I'm drawing on the bottom, I'm trying my best to keep it consistent, the wave that I'm drawing on the bottom has a much shorter wavelength than the one on the top, right? As far as sound waves go, we also will usually talk about sound waves using a slightly different measurement as well. Imagine that on the bottom of both of these graphs, I have an x-axis in which I'm measuring time. Okay. As far as time goes, what I might do is I might measure out the distance from here to here, and let's just say, give it an arbitrary number. Let's say for the sake of argument that the distance from here down to there on my x-axis is 1 second. Okay, so measuring time here, this distance is going to be 1 second. Okay. Within that 1 second, you'll notice that this wave only occurs once, right? But within the 1 second, within that same 1 second, this wave occurs, 1, 2, 3, 4, 5, 6 times, right? One of the terms that we use as far as sound waves go is we talk about frequency, okay? REM wrote a song about that. He's very concerned, asking his friend Kenneth about the frequency. No? 90s music, his references aren't landing? All right. Fine, all right. Did you get it? No? Oh, come on. All right, anyway, so nevertheless, we often talk about the frequency of a wave, okay? This wave with a shorter wavelength is a higher frequency because it occurs more times in 1 second. This is a lower frequency, right? So when we talk about high frequency sound, what are we, like what type of sound would be a high frequency sound?
High pitch.
Like a high pitch, right? We also use pitch to talk about that, right? So a high frequency sound would be something like this, right? Whereas a low frequency sound would be a lot lower of a pitch, right? So when we talk about sound waves, when we talk about frequency or the wavelength, that's something we often think about as the pitch of a sound, right? But we can also talk about the amplitude of a sound as well, right? So for instance, I might have a high frequency sound like this, and I can have the same frequency. It's hard to do. I want a voice by the end of the day. It can have the same frequency, but look at the difference now. The waves aren't as tall as they were on the other side, right? So this measurement that we use to measure the height of the wave is called the amplitude. And the amplitude of a sound wave is going to essentially tell us about the volume of the sound, right? We can have two sounds that are roughly the same pitch, and the other one is really, really loud, right? So we can talk about the pitch or the frequency of a sound, but we can also talk about the amplitude of the sound, which of course we interpret as volume, essentially. Okay. As far as sound goes, there is one additional sort of characteristic of sound that we often pay attention to. It's a lot harder to graph though. I don't know how to graph it, to be honest with you. It's a characteristic of sound that we call timbre. T-I-M-B-R-E. We're not talking about timber like a tree falling down. We're talking about timbre as a quality of a sound. How do I explain it? So timbre, imagine that you're in the orchestra room or the band room, and you've got somebody sitting at a piano, and you ask them to play a G note, right? And then you ask that same person to play a G note on the guitar, right? It's the same note, it's the same pitch, and they're playing it at roughly the same volume. But you could very easily tell me which of those notes was played on the piano versus which was played on the guitar, right? I think even somebody like me with like zero musical ability at all could tell you that, right? That characteristic of the sound, even though it's the same note, even though it's the same volume, you know which one came from the guitar and which one came from the piano because of the timbre of the sound. It's just, for lack of a better term, it's just the character of the sound, right? And that tells us an awful lot about the world. And obviously, I can't put it on a graph the same way that I can put amplitude and frequency on a graph. Okay. But nevertheless, our ear is capturing these waves, and we're funneling these sound waves using our pinna. We're funneling them into our external acoustic meatus, and those sound waves are vibrating that drum, okay, that tympanic membrane that we have in the middle of, or at the end of our external ear. So let me go ahead and put the screen back down for a second here. Look, I drew a wave going right into the ear there. That's the point, is we are trying to funnel those sound waves into the ear, right? So the bigger the funnel, the more of those sound waves that we're going to transfer in, and we're going to be vibrating or beating this tympanic membrane. In the middle ear, the next part of our ear, let me turn the lights back down a little so you can see this. In the middle ear, we're going to transfer that vibration to our 3 ear ossicles. Okay? You probably already know about these inner ear bones. They're the smallest bones in your body, but you have 3 of them. The first one kind of looks like a hammer. We call that one the malleus, and hammers usually have to hit something hard so as not to break them, even if you're hammering out a piece of metal or something like that. An anvil would be something that you would commonly use. That's going to be the incus that we see right here, and then we pass that vibration on to the 3rd bone in line. It's called the stapes, right there. So in the middle ear, we find our ear ossicles, the incus, the malleus, and the stapes. In our external ear, we have our pinna, we have our external acoustic hiatus. Again, the function here was to funnel sound. Okay. Sound waves. Funnel sound waves. But at our middle ear, the sort of junction between the middle ear and the external ear is where we find our tympanic membrane, right? So we kind of put our tympanic membrane right here. Okay. And that tympanic membrane vibrates, and we transfer that vibration to our ear ossicles. Going to be our malleus, our incus, and our stapes. So our ear ossicles are our incus, or I'm sorry, our malleus, our incus, and our stapes. And the vibration is passed from bone to bone to bone in this order, right? But all we're doing is we're vibrating that tympanic membrane, and then those bones start to vibrate. Okay? For high amplitude sounds, they vibrate really hard, and that transmits information about the volume of the sound. For high frequency sounds, they vibrate really, really fast, and that transmits information about the frequency of the sound that we're hearing, right? So we see here that we have these 3 ear ossicles. Okay? As far as actually hearing things, there's not a whole lot more that really happens in the middle ear. This middle ear is really sort of a space to transmit vibration from one bone to the other, so that we can get that information into our internal ear, which we'll talk about here in just a couple of minutes. But we do, to some degree, have to control the environment in that middle ear. Specifically, we have to make sure that our eardrum is tuned correctly, right? Again, I have about this much musical knowledge, but one of the things that I do know is that musical instruments have to be tuned in order to sound correct, right? And I believe, you guys can correct me if I'm wrong, I believe this goes for drums as well, right? Drums also have to be tuned correctly in order to sound right. Your eardrum has to be tuned correctly in order to sound right. So I'm gonna turn the lights back on for a minute. I'm gonna be all over the place today, but that's all right. It's Friday, I'm allowed. I'm gonna put the screen up for a minute. just for a minute about the air around us. So these sound waves that I'm erasing right now have to travel through the air, right? So let's talk a little bit about the air that surrounds us and our atmosphere. You guys didn't know you were going to get an atmospheric science lesson today, did you? Let's get real though. You paid for your whole seat in this class. Today, you only need the edge. I'm joking. All right, let's go ahead and talk a little bit about the world around us. All right, so we're in Riverside. We're not terribly far from the ocean right now. And some of you might actually be going to the ocean this weekend, right? So if we were to sort of draw that out, you know, here's the ocean right here. And the ocean conveniently has an elevation of 0 feet, right, below sea level as a result of that. But, you know, when you leave the ocean, even if you only leave a little ways, you come up on land, okay? And if you come in far enough, you might end up here in Riverside. Does anybody know what the elevation is here at RCC, roughly? How far above sea level we are? Yeah, have any idea? Am I the only person that asks these things? It must be like a total dad thing. I like roll up someplace and I'm like, what's the elevation here? We're at about 800 feet elevation here at RCC. Pretty darn close anyway. Might be a little bit more, a little bit less, but if you live over on the other side of town, closer to Moreno Valley, you're actually quite a bit higher than we are here. You know, you have to go up a hill no matter how you get to that part of town. And that's about 16, maybe 1,700 feet on that side of town. But here at RCC, we're at around 800 feet of elevation. UCR's around 1,200 feet, I think, maybe 1,300 feet, something like that. Fun fact, you guys know UCR is the highest elevation UC campus in the UC system. That's why they're the Highlanders. That's how they get their mascot, the Highlanders, because they're the highest elevation UC campus. Maybe you guys knew that before today. How many of you guys have been to UCR? Did you go there for school? Yeah. Are you going to go, maybe? Well, now you know a fun fact about UCR. Do you know what the second highest elevation UC campus is? You want to guess? I bet it'll surprise you. The second highest elevation UC campus. It's not Berkeley. I think Berkeley is lower than we are, actually.
Irvine?
Not Irvine, that's a good guess. I heard, who said it in the back over here? You gotta go surprisingly close to the water to get to the second highest elevation UC campus. It's Santa Cruz. Santa Cruz is the second highest elevation UC campus because it sits up on the bluffs above the ocean. So, again, you learned something new today. Their mascot is the banana slugs, and it has nothing to do with their elevation. Anyway, Riverside, around 800 feet elevation, okay? But you know that you could go higher than this, right? You might be going to the beach this weekend, but you might also be going to the mountains. Maybe you decide to go to Big Bear or something like that over the weekend to hang out for a little bit. So you can take a drive up the hill and you can go a little bit higher than that, right? We'll go ahead and do it this way. Do that. This is Big Bear Lake right here. Big Bear Lake, you can maybe go up to the water up there. You can even go higher than that if you want. Right? If you get really ambitious, maybe you can go climb Mount Everest or something like that. You probably don't have time this weekend because you have a test next Friday, but you could still maybe go climb Mount Everest or something like that. So if we wanted to do that, Mount Everest is right here. Okay. All right. Mount Everest is 29,032 feet above sea level. So it's up there. Let's make this Big Bear, right? This is not to scale, by the way. Big Bear is what, around 7,000 feet elevation, something like that? I don't know. I just know when I go up there to ride my mountain bike, I definitely feel the change in elevation. down here. But nevertheless, this is about what we have, right? So we know that we can go to higher elevations, we can go to lower elevations, and so on and so forth. So you and I are here in Riverside right now at around 800 feet elevation. There you are. If you go up to Mount Everest, you might be up there like this. If you do that, you'll have to put on a stocking hat because it's cold up there, right? So you've got your stocking hat on top of your head, right? Okay, so tell me, now that we understand that our world changes elevation, I guess we can add one more thing to this. Let's do that before we go any further. At some point, you go high enough, you're going to run into space, right? You're going to run into the edge of our atmosphere. So let's go ahead and just kind of put a hypothetical edge of our atmosphere up here. This is about as high as you can get. Obviously, when you're on the summit of Mount Everest, you're way closer to the edge of our atmosphere than you are down here in Riverside, right? Okay, now that that's all established, tell me a little bit about the air that we breathe, okay? We're surrounded by air, okay? And it has a certain makeup. So as far as the air that you breathe goes, what's the most prevalent gas in our atmosphere? Definitely not oxygen. I know, we would think that, right? It's an important one. It's the one that we talk about the most. But the most prevalent gas is what? Nitrogen. Yeah, it's nitrogen, right? In fact, our atmosphere is about 79% nitrogen. Okay? So in the atmosphere, the air that you breathe right now, when you bring in a breath of air, 79% on average of the molecules that you're bringing into your lungs are nitrogen. Okay? Nitrogen, N2. Okay? We know what the percentage of oxygen is in our atmosphere. What? 9%. 9%? A little higher than that, but it's not a whole lot. It's actually about 20.9. I'm gonna be a little bit more technical. I usually sometimes round it up to 21, but it's about 21% oxygen. 20.9 to be a little bit more specifically. I think it's like 20.93 or something like that. But we'll go ahead and round it. Can't be too high, otherwise we would have exploded a very long time ago. Anything over about 30%, and things tend to go boom very easily because oxygen is an exceptionally flammable gas. Anything lower, and we probably wouldn't be able to sustain life. So looks like Earth found a sweet spot, which is good for us, right? But if you're doing math along with me, you're adding up 79% and what's essentially 21%, and you look and you say, these two equal 100%, right? That means everything else in our atmosphere is way less than 1% of the composition, right? So we're going to go ahead and add that here. We're going to say less than 1% of what I'm going to call inert gases. Inert gases include things like carbon dioxide, okay? What is carbon dioxide's percentage in our atmosphere is like 0.03%, something like that. It's rising as the climate changes. It's rising, but it's something like 0.03%. I need to double check that. We usually talk about it in parts per million, which is slightly different than the discussion that we're having here, but something like that. But nevertheless, inert gases, carbon dioxide. Argon is another important inert gas in our atmosphere, and things like that. The big two are going to be nitrogen and oxygen. Okay, these two are the big ones. Just so happens that nitrogen reflects blue light, and that's why our sky is blue, is because nitrogen reflects blue light, and it gives our sky a blue color, right? So there's a good reminder that nitrogen is the most prevalent gas in our atmosphere. Okay. Just out of curiosity, what do you guys think the percentage of oxygen is on the summit of Mount Everest? What? Okay. Do you have a number in mind? Hard to breathe up there.
5%.
5%. Okay, all right. Trick question. It's 20.9%. Doesn't change. Some concentration of oxygen in our atmosphere, or the percentage of oxygen in our atmosphere, is the same everywhere on Earth. Our atmosphere is our atmosphere is our atmosphere. We'll talk more about Mount Everest when we talk about the respiratory system later on in the class. But just remember, it's going to be a trick question when I ask you again in a couple of weeks what the percentage of oxygen is on Mount Everest. 20.9%. Everywhere on Earth. Doesn't matter if you're at the ocean, whether you're way up in the mountains, still 20.9%. Okay. Nitrogen, oxygen, carbon dioxide. Those are all elements on the periodic table. Do those things have mass associated with them? They definitely do, right? They are matter, okay? They just happen to be in a gaseous phase, and that's why it's air instead of liquid nitrogen that surrounds us or something like that, right? But they definitely have mass associated with them. So as I, in Riverside, stand here at 800 feet looking up, pretending I'm looking through the ceiling of the building and out into space, I'm looking up at the edge of my atmosphere, and I see that there's a column of gas that's pushing down on me because they have mass, right? So these gas molecules, 79% of them are nitrogen, 20.9% of them are oxygen, the rest of them are other things. They're all going up here to the edge of the atmosphere, and they're all pushing down on me because they have mass, the same way that you have mass, okay? When they push down on me, we call this our atmospheric pressure, okay? So this column of gas pushing down on me is called my atmospheric pressure. Another dad thing to ask, right? What's the atmospheric pressure today? Because we seem to care about that. My dad does, anyway. Every time I call my dad on the phone, he says, "How's your weather? What's the atmospheric pressure doing?" He does. I'm not joking. He actually asks me that. But he grew up on a farm, and those sorts of things matter because we can predict the weather based on changes in atmospheric pressure. We're not too worried about that today. You can take an atmospheric science class if you're interested in that. But we are concerned about the atmospheric pressure because there is this column of gas pushing down on us. Do we know what the atmospheric pressure is at sea level? What is it? It's 760 millimeters of mercury, right? So at sea level, the atmospheric pressure is 760 millimeters of mercury. Okay, which happens to be equal to 1 atmosphere. Okay, we can also measure pressure in atmospheres. 760 millimeters of mercury is equal to 1 atmosphere, or ATM. Oh, it's not a very good M. Let's fix that. 1 ATM right here, right? 1 atmosphere. Okay. I think they designed it that way. 1 atmosphere would be exactly the pressure at sea level. This can obviously change. It isn't a constant thing that's completely unchanging, and it does definitely change with weather, right? So we talk about high pressure systems and low pressure systems and things like that. But on average, the atmospheric pressure at sea level is about 1 atmosphere. You and I, in Riverside, aren't that far above sea level, at least in the grand scheme of things. The pressure probably isn't terribly different here in Riverside either, right? We could look it up, but it's probably not a whole lot different. But when you go to Big Bear or you go to Mount Everest, the pressure definitely changes. So, column of gas up above you going all the way up to the edge of the atmosphere. As you go to Big Bear, does that column of gas get taller or does it get shorter? It gets shorter, right? As you go to the summit of Mount Everest, it gets even shorter, right? So, does the atmospheric pressure increase when we go up in altitude, or does the atmospheric pressure decrease? Remember, it's the result of that column of gas pushing down on you. So as you go up in altitude, the column of gas gets shorter, meaning that there are fewer gas molecules pushing down on you. The atmospheric pressure decreases, and the atmospheric pressure decreases. I don't remember the exact numbers. I think the atmospheric pressure on the summit of Mount Everest is somewhere on the order of about 250 millimeters of mercury. So it's significantly less than it is at sea level, right? So as we go up in altitude, the atmospheric pressure decreases. Okay, so what the hell does this have to do with our middle ear? Okay, let's go ahead and talk about that. All right, so your middle ear is separated from your external ear by your eardrum, your tympanic membrane. Okay. This side of your tympanic membrane is open to the environment, right? There's nothing blocking it from doing this. So what that means is that this side, the external side of your tympanic membrane, the pressure is always equal to atmospheric pressure. Regardless of what atmospheric pressure is, this side is always equal to it because it's open to the environment, right? So let's just say that we're at the beach right here, 760 millimeters of mercury, okay? But then you just get in the car. You're gonna get in the car tomorrow. You're gonna take a drive up to Big Bear. As you drive up the hill, the pressure starts to decrease, okay? In here, this is still 760 millimeters of mercury because it's equalized with atmospheric pressure. But over here, so I'm going to go ahead and do this. This is equal 760 millimeters of mercury. But as you get in the car and you start to drive, this number is going to start to decrease, and you eventually arrive up in Big Bear. I don't like to make things up. Let's look at Big Bear City, California, atmospheric pressure. Because we can look this stuff up. Number 29.94 millimeters of mercury, inches of mercury, 29.94. Inch to millimeter. Right? Comes out to exactly 760. That's definitely not right. It's definitely less than here, so something isn't right there. Either way, what we'll do is we'll just go ahead and guesstimate. We'll say that this goes down to maybe 600 millimeters of mercury, which is probably a little bit more accurate, right? So what we see is there's a change, right? As you get up and you drive up, this changes, okay? So that means that that your tympanic membrane isn't tuned correctly. As a result, you're not going to hear things the same way. You've definitely noticed this as you've gotten in the car and you've driven up in altitude. You don't have to go all the way to Big Bear to experience it. But how do you feel when you start to drive up the hill, as it were? You feel like you have to pop your ears, right? That pressure starts to build, that pressure difference starts to build, and it starts to affect your tympanic membrane. It can be painful. It definitely feels like there's a pressure difference in your ear. And you also probably notice that things don't sound the same. Your voice doesn't even sound the same when you talk because that tympanic membrane isn't vibrating correctly. Okay. So what do we have to do? We have to equalize the pressure. And the job of that is this structure that we see right here. This tube that we see right here is called the pharyngotympanic tube, right? So this is another important feature of the middle ear. It's called the pharyngotympanic tube. It's a long name. It's also called the auditory tube, which is shorter, but I like this one because it's more descriptive. It tells me where the tube goes, right? It goes between essentially what we used to call the tympanic space. We now call it the middle ear. But it goes basically from the middle ear to the pharynx, which is your throat. Okay? Your throat is also open to the environment. The atmospheric pressure in your throat is always the same as atmospheric pressure as well. This pharyngotympanic tube is normally lies fairly flat, okay? There's not a whole lot of cartilage or structure or anything like that to it. So normally the tube just lays kind of flat, right? But occasionally when you yawn or you do this, you start making the funny faces when you have to pop your ears, right? Or you chew gum or something like that. What you do is you can pop that tube open a little bit. And when you do that, what it does is it equalizes the pressure with atmospheric pressure. So now, what you've done by opening that pharyngotympanic tube is you've popped your ears. You've equalized the pressure on both sides, and now your tympanic membrane can beat the right way, can vibrate the right way, and you start to hear normally again. And pressure goes away, etc., etc., etc. Okay? So that pharyngotympanic tube is really, really important because it allows us to equalize the pressure on both sides of the tympanic membrane. Okay? Of course, when you go down the hill, right, you had your fun in Big Bear, now it's time to go home. The exact same thing happens, only in the opposite direction, right? Now the pressure on the outside starts to increase as you go down in altitude, and we see that again we have a pressure differential on both sides of the tympanic membrane. You have to equalize the pressure again, and you pop your ears once more, and all is right with the world. Okay, so that's an important feature of the middle ear, and it definitely affects our sense of hearing. Kind of as an aside from that, our pharyngotympanic tube does like to act occasionally like a little superhighway between the throat and the middle ear for viruses and bacteria and things like that as well. So it's not a terribly uncommon thing for us to see something like strep throat turn into an ear infection, right? Because those bacteria like to crawl straight up that little passageway and they get into the middle ear and they cause an ear infection. And we have to take antibiotics to be able to get that infection out of there. Right? So there's a little bit of an additional sort of a health thing related to that as well. Okay. I know it's kind of a long lead up to a fairly small anatomical structure, but this is going to come back up when we talk about the respiratory system as well, because air pressure matters when we talk about the respiratory system. So this will be here for a while with us. I just wanted to get it out of the way today. So the transmission of sound goes from the tympanic membrane, which is vibrating in response to those sound waves, to the malleus, the incus, and the stapes. They're vibrating, and then what they do is they transmit that vibration into our internal ear that we see right here. And we see that structure is ostensibly more complicated than what we've seen so far. We're going to dive into that a little bit more later on this morning or this afternoon. Really quick though, just to kind of point this out, the stapes, oops, this isn't lab, I can't draw on the board like I was. Forgot what it was. The stapes is going to kind of be right here. There's a flat end to the stapes, and there's a membrane right there. So there's a membrane here, the tympanic membrane. There's a membrane here on the other side of the stapes that you can't really see here. It's called the oval window. Okay? And the oval window is a membrane that's going to vibrate again. Right? So we see here that we have the oval window. The oval window leading us into the internal ear. Okay? And that's where things get a little bit more, like I said, a little bit more complicated, a little bit more involved when we start to take a look at this. So let's go ahead and take the screen down again here, and let's take a look at what we have in the internal ear. Okay. Jesus, 50 minutes and I haven't made it past my first slide. Let's just zoom through. All of this is what I've been saying for the last hour. It's all already in the notes. Okay. Okay. Real quick, this slide is kind of helpful. I can't really draw the same way that this slide sort of shows this. In that middle ear that we've been talking about with our three ear bones, this is looking at them from a slightly different angle. There's the tympanic membrane right here, and now those ear bones are sort of facing you. There's a couple of muscles in the inner ear that are attached to those ear bones. The biggest one, the one that's going to be the easiest for us to see in lab, is this one called the tensor tympani muscle that we see right here. Most of the models of the ear show that tensor tympani muscle really, really well. And then the other one that's really quite small, and I looked yesterday again at our models, I don't see this muscle on those models. It's called the stapedius muscle. It's right here. Really, really tiny little muscle, like literally just a couple of muscle fibers. What these muscles do is they work to essentially kind of control how hard these bones vibrate, right? I suppose that it's conceivable that you could have a sound that's so loud, an amplitude that's so high, that you could vibrate these bones so hard that you could cause them to break, right? I think we all know that if bones hit something hard enough, they can actually break. This happens to us on a fairly regular basis. We don't want that to happen to these little ear ossicles. It would make it very difficult for them to heal. So what these muscles do, this tensor tympani and the stapedius muscles do, what they do is they can contract in response to loud sounds, and they can prevent those bones from hitting each other so hard, and that prevents damage to those bones. So it's a little bit of a protective measure in the middle ear to help those bones from being broken, because that would be not very good. It also prevents really loud sounds from getting transmitted into the inner ear. Now we know that loud sounds can definitely dampen our hearing over time. We'll talk about how that works in the inner ear when we get into that in more detail. But at least in the middle ear, we have a small ability to sort of dampen sound with these two muscles that we see here and right here. Okay. Any questions so far? Okay. That does lead us to the inner ear. We have this fairly complex structure in the inner ear. It's kind of divided in half. The upper half, at least in this diagram, has these three large circles that are associated with it. And then the other half of it looks kind of like a snail shell, right? You see this structure on the other side of it. This entire structure is what we call the bony labyrinth. Okay, we have multiple models of the bony labyrinth in lab that you guys will be able to take a look at. A labyrinth, as you guys probably know, is like a maze or something like that, right? So this is kind of a maze-like structure with lots of different passageways and things like that that we can explore. So far, we've talked about the external ear and the middle ear. Both of those structures have only to do with hearing, okay, our sense of hearing in the external and the middle ear. Obviously, we're going to complete that process here in the inner ear, but we also find our sense of equilibrium or balance in the inner ear as well. Okay, so part of this bony labyrinth is going to function in equilibrium and balance. Part of this structure is going to function in hearing. Okay, so if we wanted to sort of put this up on the board over here, just to kind of remind us of that. So all three of these structures have to do with hearing. This one has to do also with spell that right? Yeah, hey, cool. Okay, so the internal ear serves sort of a dual purpose, and we'll talk about both of those senses kind of separately from each other because they do function more or less independently. So we have this bony labyrinth. on this side of it, we call these circles, we call them the semicircular canals. You have 3 semicircular canals. You have the anterior, the posterior, the lateral. I'll show you on a model in lab which one is which. I'm not going to expect you to remember it from this diagram. And this is the part of these semicircular canals are the part of the bony labyrinth or the labyrinth that deal with equilibrium. Okay. The snail shell shaped structure that we see over here, this is called the cochlea, and the cochlea is involved in our sense of hearing. Okay, so we have our 2 different structures over here. One is involved in our sense of equilibrium, and the other is involved in our sense of hearing. Another thing that you'll notice about this structure is that it is made up of bone, and like I said, we have several models in lab that are going to illustrate this for you. Additionally, though, the entire bony structure is lined by mucous membrane, mucous membrane that we call the membranous labyrinth. So that's what this kind of blue color is meant to show, is that we're lining the entire thing with this membrane called the membranous labyrinth, right? So the outer part, the bony part, is called the bony labyrinth. The inner membrane that we find is called the membranous labyrinth. Okay. And then we see here that this is sort of the entryway to the labyrinth. This is the stapes kind of coming from the middle ear right here. Everything else would be here. That's that membrane, that oval window that we have. And then we sort of enter the labyrinth right here. An entryway, if you guys have an entryway in your house, maybe you like to camp and your tent has an entryway on it, it's often called a vestibule. Okay? A vestibule is not really a word that we use a whole lot anymore for home entryways, but it is a term used to describe an entrance, right? So we notice when we get into this, we notice that we have this kind of open space right here. This open space in that bony labyrinth is called the vestibule. Okay? And that's where we can either go to our semicircular canals or we can go to the cochlea over here. All right? So we're about out of time, but when we get into the lab, we're going to start to talk about some of those membranous structures